So we have seen how to transform a robust set of constraints into standard constraint by using the dual of the problem that is equivalent to the constraint. So let's see what it means on a number of cases. So let's restart with Here we are. Let's start with this quiz, which is a bit sophisticated, but it's worth spending some time understanding it. So let me first resurrect Speak Up. So while Speak Up is trying to start, here the title says, I have a condition on C. The condition on C is that the inner product of C and X is less than 3.14 for all value of X that satisfy the following inequalities. So this is a polytope in n dimensions, and we say the vector C is such that the inner product with any X in this polytope is less than this bound here. And I'm proposing 3 equivalent formulations, which, if any, of this formulation is equivalent to that. So let me close this poll. The majority says D, which is the correct answer. So the first thing to realize is that this condition is equivalent to that one that bears into an optimization problem. We say that Cx is less than 314. That means the worst case of this must be less than 314, and the worst case is the largest value that is possible when X takes all the values that are here. So A is now our classical reformulation where the quantifier whatever is replaced by a maximization. And now by duality, if we compute the dual of this problem, we will find a condition which leads to exactly this. The mean of the dual problem, these are the constraints of the dual problem. And the objective function of the dual problem is B transpose lambda. Remember that in duality, C takes the role of B. A becomes A transposed. So this is exactly the very first example we had before. That's the symmetric dual problem. Any dual problem in this form, any linear program in this form is dual is symmetric. So this is exactly saying that, which is completely non-obvious. It's saying that X satisfies this constraint is equivalent to saying that there must be some value of lambda that satisfies this constraint, such that the inner product of lambda is less than 3.14. So this has a name. This is an instance of what is called Farkas lemma, but you don't need, in fact, to know Farkas lemma. All you need is to know now the standard transformation of a linear program and its dual. So why did we do this somehow technical excursion into duality and its beauties? Well, it is because it is quite widespread to use what is called linear controls, or more precisely, affine disturbance feedback control. What is this? In the exercise we saw before, we said there will be loads, they are more or less certain, and we will fix value of G2 and G3. And in fact, the only thing that adapts is G1, is the slack bus that adapts not because of our control, but because of its nature of slack bus. There is a controller in this generator that makes sure the voltage is constant, and by doing that, it will automatically be the slack bus and satisfy the power balance here. However, of course, if we can do a bit better, we would be more happy. In particular, is it a good idea to choose the set points of G2 and G3 once for all in the following day, in the previous day, given that we don't know exactly the value of L1, L2, and L3. So it would be better if, instead of having fixed set points, we could have what is called a policy. A policy means the parameters of a rules that will say instantly what the values of G2 and G3 would be if we can, for example, measure somehow, directly or indirectly, the values of L1, L2, and L3. So this is very commonly done in grids. In fact, all grids today work with one form of linear control, which is called droop control, which is not as simple as what I showed here, but droop control adapts the generators to the fluctuations of the load using a signal, which is the frequency of the grid. Here, we will not go into this excursion. We'll do something simpler, but morally speaking, it's equivalent. Assume, for example, we want generator 2 to be adaptive. We probably want to do generator 3 as well, but to simplify the story, I will do it only for generator 2. And if we wanted to have it adaptive, there are zillions of ways to do it. One simple way is to have linear control. So the idea is to have G2 equal to some fixed value, like we did before, plus a gain multiplied by the true instantaneous value of the disturbance. So if we do this, we are in fact adapting to the disturbance here. So this is what is called affine disturbance feedback. Affine because it's linear plus constant. That's what affine means. It's a feedback because we react to the true value of the disturbance, and disturbance feedback because the input into the feedback is the disturbance here. So other than that, once we have put this together, then we can apply directly all the techniques we've seen so far. So for example, if we want to minimize average cost, we could say the forecasted value of generator G2 will be what? Well, it depends on the disturbance, but in a linear way. So the expected value of G2 will be U2 plus V2 times this. Now, U2 and V2 are my control. Instead of choosing the value of G2, I would choose U2 and V2. The actual value of G2 will be its mean value plus this. That is another way of writing exactly the same as before, but here I've expressed the unknown part of the disturbance, the deviation from its expectation here. So we see that the true value will be the fixed value, like we had before, plus it will adapt here to the whenever the true value L1, L2, L3 is revealed here. Let's apply what we've seen before here in the case of robust OPF. We could take the expected value, but to simplify the story here, or to illustrate everything, I will do the worst case cost. So that means, I will take the expected cost, sorry. So what are the control variables? U2, V2, like we've said. Now G3 in this simple exercise is not adaptive, so we still need to find a fixed value. This is our control variable. The disturbance is the same as before. The state that is a function of both the control and the disturbance are the angles with the DC approximation and the resulting slack power G1 here. The expected cost, if everything is linear, will be simply given by those values here. So here we have G2, Here, I realize that this is a bug. If I do in per unit, that should be 7. So this is the expected value of the coefficient in front of V2 here. So this is using the formulas that we have given before. So we have an expected cost here. Now the constraints are similar. The constraint, for example, on G1, the slack bus power constraint, except now we see that they depend on G2 and G3 and the loads, but G2, through these linear control forms, depends bilinearly on the disturbance, L1, L2, L3, and the control here. And the same is true for the branch power flows here. So we have a problem that would be embarrassing if we hadn't done what we did just before the break. It's a problem where the robust inequalities have a bilinear term. But fortunately, we know how to do that, at least in theory. Let's do it for the first constraint. So the first constraint is this one. It's saying that the value of G1, the resulting slack bus power, must be larger than or equal to 0. So then here, it means that, so this is the value of G2, this is the value of G3, and this is the sum of the loads. This is the constraint we obtain here. So we have one constraint with the disturbance L1, L2, L3, which is itself constrained by 6 inequalities. So I have to add one vector with 6 components, two which are the dual variable that corresponds to the theory we said before. I add the constraints that are given by the transformation of my linear problem. So I skip some of the details. We need to apply exactly the framework that is before, identify the matrices, and that gives us this constraint, similar to what we did to the quiz just before the break. So we have those constraints on the lambdas, they must be non-negative, and this additional constraint here that replaces this one here. So we replace one inequality with must be true for any value of the disturbance by this inequality plus 6 variables that themselves come with their constraints. But now we are saying those are variables we can add to our optimization problem here. So we must add this and do as many as we have as necessary. By the way, how many vectors of dual variables will we need to add? Close the poll in 5 seconds. The correct answer is 10, which is also the majority choice. Because that's the number of inequalities where the disturbance appears in the coefficients of the optimization variable. So of course, there are inequalities on the right and on the left. You need to count all of them. That's the kind of things you need to do when you apply this theory. If we cast that in this framework here, what are the dimensions of the matrix D? close the poll in a few seconds. And here the correct answer is C. It has 6 rows and 3 lines. The vector D is this one. There are 6. So D has 3 columns. This is the number of dimensions. But there are 6 inequalities on D's because we have 2 inequalities per component of D. So there are 6 inequalities in total. So if we sum up all of this, we've transformed our non-robust optimization problem into a robust one into a standard one. But how many optimization variables do we have at the end? I close in 5 seconds. I close immediately. And the correct answer is 63. So in the lab, in the next lab, when you will do some robust stuff, that's exactly what you will need to do. So if we compare to the size of the original problem, there was 3 variables. Now there are 10, 3 because there were 2 generators and 1 had 2 coefficients. And now we have 63. So that's the price to pay to making the problem non-robust. So this is why also in practice, this works well if everything is linear. Making the problem very large dimension and non-linear might be an issue. To conclude on this, here is what happens if I do exactly the program I mentioned. So with my 63 variables, I solve the problem and I plot the optimal expected cost as a function of the uncertainty on the disturbance. So I did the same thing. I increased the uncertainty linearly from the original bounds I had here to something that increases here. Then, like before, I see that there is a point after which the system becomes unfeasible. So the additional constraints that I add become unfeasible. So the true cost becomes infinite. So which means we're not able to control the system. There's too much uncertainty. However, if we compare to the non-affine feedback case, this is what we had before. We've doubled the range of uncertainty over which we could go. The cost is less. That's the first observation. And second, we see that before, when the uncertainty on L3 was 100 megawatts, then the robust formulation did not work anymore. Here we're able to quasi-double the range here. So that is, of course, the interest, and this is why we do it. Having a feedback policy when we need to control a very uncertain thing, even with simple things like linear feedback, very often is quite efficient. That's the end of today. So in summary, handling uncertainties leads to problem with control and disturbance. Perhaps the most important and the most difficult thing is to have the framework correctly in place. So I've tried to go through many small steps to put the framework piece by piece. There are variants in what people do and what we can do and what we will do in the lab. We can minimize the average cost or expected cost versus the worst case cost. And one of the issues is when we have worst case, for example, is how to remove the max, but this we've seen is fairly easy once we know the trick. A bit more difficult is to remove the fact that the constraint must be true for every value of the disturbance, which may be true with high probability if we use chance constraint or strictly speaking otherwise. And there are systematic techniques, at least when everything is linear.